Hey everyone, it's Justin again. In this video, you're going to learn how to solve systems of equations using a new method, substitution, just in case you don't want to use the graphing method. Substitution connects to a skill we've practiced many times already, plugging in for a variable. First, take one of the equations in the system and isolate a variable. This is just like solving for y to change an equation to slope-intercept form. Then, replace that variable in the other equation with what you just found that it's equal to. Then you solve for whatever variable is still there. Now, take that variable you just solved and plug it in for either of the original equations. This will allow you to solve for the variable that you didn't solve for before. These steps seem a little wordy and confusing, but once we do a few examples, you'll understand them a little better. One thing to realize is that it gets a little easier if a step is already done for you. That's why we usually use a substitution whenever one of the equations already has an isolated variable. That'll cut out the first step automatically. So let's try an example. As you can see, the first step is already taken care of. One of the variables, y, has already been isolated. Next, we'll take the other equation, x minus 3y equals 6, and substitute 10 minus x in place of y. Notice how there's only one variable now. That x is what we're going to solve for, just like the regular multi-step equations we've solved. We distribute the negative 3, combine like terms, and add 30 to both sides, and finally divide by 4. Now we know that x has to equal 9 in our solution. Before we continue, notice what we did at this point here. We took the first equation and substituted it into the second equation, effectively combining both into one equation with a single variable. This is where the substitution method gets its name, all right? Now let's finish solving this system. Our next step is to plug in the variable we just solved for, that's x, into either one of the original equations. To prove that either equation is okay, I'm going to use both of the original equations. For the first equation, if we plug in 9 for x, we get that y is 10 minus 9, which is 1. And if we use the other equation instead, we plug in 9 for x, subtract 9, and divide by negative 3, and we still get that y is 1. So it really didn't matter which equation we plugged into, they both gave the same answer. Usually you just want to use the simpler equation here, so we could have just used the first one. So, what's the solution to this system? The point where the x-coordinate is 9 and the y-coordinate is 1. You didn't think we were done yet, did you? We have to find a solution, but we want to make sure it's the right solution. Remember, the more steps you take, the more opportunities there are to make a mistake. There were a lot of steps in this problem, so we want to double check our answer in case we messed up one of the steps. So what is the solution to a system supposed to do? Oh, right. When you plug it in, it makes both equations true. So if you plug in 9 for x and 1 for y in the first equation, it's pretty obvious that it's true. 10 minus 9 is indeed equal to 1. And for the second equation, if we plug in the 0.91, and simplify a little bit, we get that 9 minus 3 equals 6, which is also true. Since our answer caused both equations in the system to be true, we can be doubly sure that our solution is correct. For this next example, neither variable is isolated yet, so we're going to have to do that first. We can isolate for any variable from either equation, but we want to use one that is the easiest, so we'll have less room for error. Isolating r in the second equation takes only one step, adding 2q to both sides. So let's do that. Now that we've isolated a variable, we can substitute it into the other equation. Now, despite how complicated that looks, our new equation has only the variable q, which we can solve for. First, combine like terms inside the parentheses. Then distribute the negative 3. Then add 3 to both sides. Add 6q to both sides. And finally, divide by 7. Whew, that took a lot of steps, but we finally figured out that q is -3. Now we take that value and plug it into one of the original equations. The second equation is simpler, so we'll use that one. Plug in -3 for q, and then simplify, and we get that r is -2. Let's make sure we didn't make any mistakes. First, we plug in our answer to the first equation, simplify, and we see that the equation is true, meaning -2, -3 is a solution for the first equation. If we do the same for the second equation, we also get a true statement. So that point is also a solution for the second equation. Because -2, -3 is a solution for all the equations, that means it's the correct solution to the system. Here's our next example, and ooh, good, a variable is already isolated, so we can skip the first step. All right, let's use the isolated variable in the second equation and substitute it into the first equation. Wait, what? Where'd the x go? Why does it say 21 equals 5? That can't be right. Substitution isn't working, so let's just try graphing it and see why. Oh, that explains it. The reason we got such a weird result is because there isn't a solution. Anytime you get an impossible result, like 21 equals 5, that means there's no solution. A system that's impossible to solve will result in an impossible statement. So then this system has no solution. This is going to be our last example. Again, we can skip step 1 since the first equation already has y isolated. So take the second equation, substitute for y, and simplify. And of course, we get another weird result. You know the drill. Let's graph it, see what's going on. What? Where's the second line? Ah, there it is. The two lines are actually the same line. And you know what that means? Infinite solutions. So if substitution results in a weird, always true result, that means the lines are always intersecting. So there are infinite solutions. So then this system here is made of overlapping lines and has infinite solutions. Substitution is super helpful if you don't feel like searching for graph paper, and it's especially useful when one of the equations has an isolated variable. This is only the second method for solving systems, though. In the next lesson, you're going to learn the final method. See you then.